Alright, hello and welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So what we're going to do today, we're going through this again series of verifying some frequently asked problems in both mathematics and also in chemistry. And today specifically, we're going to focus more so on the chemistry. If you're tuning in from Canada, we're looking at basically any questions you find in the grade 10 to about the grade 12. In the grade 12 curriculum, and then if you're tuning in from the US, it's about junior level and senior level chemistry. Again, my name is Joey. I'm currently a Ontario school educator. We're kind of working with OneClass. My teachable subjects are mathematics and our chemistry as well. So let's get to it. Our questions for today. Again, we have about 10 problems in ranging from high school chemistry, so from grade 1 to about grade 12. So let's get started on the session for today. Okay, so first question is asking us, a solution containing a mixture of metal cations was treated with dilute hydrochloric acid, so HCl, and no precipitate was formed. Next, H2S was bubbled through the acidic solution, a precipitate formed and was filtered off. Then the pH was raised to about 10, and H2S, hydrogen sulfide H2S, was bubbled through the solution. A precipitate again formed and was filtered off. Finally, the solution was treated with sodium carbonate solution, which resulted in no precipitation. Which metal ions were definitely present, which were definitely absent, and which may or may not have been present in the original mixture. So this problem is really asking you a couple of things. Is asking you to recognize your solubility chart. So if we have our first question here, and let me so make this a little smaller. Yeah. So if I had, so what we're doing is, again, we have a mixture of metal cations, and we have these guys here. So we have all these cations here, and what we're going to do, we're going to treat it with HCl. So we have HCl plus, we have some type of cation here. So maybe I'll just write Z in this case, Z plus. And then this is going to yield, I have Z and then Cl plus H2, because then you're going to get some gas here. But it's also saying next H2S was bubbled through the solution. So that means for this cation, we know there's going to be a sulfide as the anion. So what we can do is we can actually, we can rewrite this as HCl plus Z, and then bond it with the sulfur. But again, we don't know how many, Z here is just the metal in this case, and we don't know how many sulfurs there are, and you make H2S plus ZCl. And this here is very, very important here. But it's saying here, next H2S was bubbled through the acidic solution, and the precipitate was formed here. So it says precipitate was formed and filtered off. So in this case here, ZCl could be one of our precipitates that are being formed here, with the metal here. So we're mostly focused on this guy and whether or not it's soluble or insoluble. So we care about if it's insoluble or soluble. It's asking if precipitate is formed here. So that's really important. So in this case here, it's going to be insoluble. For if a precipitate were to be formed. And then what we're doing is we're raising the pH to about 8, and then H2S was then bubbled off through the solution. And again, a precipitate again was formed and it was filtered off. So now we're raising the pH. So you can think of it as we're raising the pH of in solution. So you can think of it as we're not treating it with dilute hydrochloric acid. We're treating it with maybe some base. And then it was finally treated with sodium carbonate solution. So sodium carbonate is Na2CO3, and then which resulted in no precipitation, which means it's going to actually be fully in be fully in solution. So I'm going to add some type of compound that we make here. So this will be our I'll just write precipitate here. And this results in no precipitate. So everything is in solution here. So it's asking us, again, which metal ions were definitely present or were definitely absent here. So basically what we're going to do is we're going to look at our solubility chart. And it says here, we want to look at this first step here because we're treating this metal cations with dilute HCl first and no precipitate formed. So when we're looking at Cl here, we know HCl here is going to be our anion, or Cl here is going to be the anion, and the metal is going to be our cation, right? We have all these metals for our cation here. So it says in Cl minus, it's actually soluble, which is good, except for these compounds. So we have silver, mercury, and lead. So we have silver, which is this guy here, mercury, which is H2 plus, and Pb2 plus, which is going to be our lead here. So let me break that down. So basically ZCl is soluble, however it's not soluble or it forms a precipitate when we're in Hg2 plus, Pb2 plus, and also G plus. But everything else is soluble, which is great. And then it's asking us, then the pH was raised to about 8, and H2S was again bubbled through the solution. A precipitate again formed and was filtered off. So we can, so what we have here would be, so again, we're adding this H2S again, and we are adding it with the insoluble solution. So it's either mercury, lead, and silver here. We're adding it to the H2S solution, and then we're going to make another compound here. So let me write that down. So in this step, and I'm not going to confuse with this step, so we have again, so we either know we have these three cations, so maybe I'll make this a YCl plus H2S, and then we're going to get back HCl, right? So we get YS plus HCl. And YS here is really, really important because it depends if it's mercury sulfide, lead sulfide, or silver sulfide here. So if we look at our compounds here, it says this is going to insoluble, right? And as you can see, precipitate formed again, which is good, and was filtered off. So now we know that it's insoluble except for group 1 here. 2 and 4, and these guys here are all transition metals, so you don't have to worry about that, which means that they're actually all this could be all part of the solution here. And finally, it's treated with sodium carbonate here. So we have this compound, so we have YS plus Na2CO3, and this is going to get me and simply just a double displacement reactions, right? So I get Y. Don't worry about balancing here because we don't really know the compounds. So Y carbonate plus NaS here, or Na2S. Sorry, this one we can do sodium sulfide and something carbonate here. And we know Y here. If you look at our solubility chart, we have our carbonate here, right? So it says insoluble except group 1A and NH4 plus. So except 1H4 plus, and it says here. It results in no precipitation, so it's actually going to be part of the solution. So what we can do here is I'm just gonna check the answer here first. And it says the first group of metals precipitate in dilute HCl. Oh, these are 3 solutions. Okay, that makes sense then. So these are 3 separate solutions. Okay, so the first one. So actually, these guys are all going to be separate. So the first solution we stated here, right? These guys are our compounds here. So it's just mercury, lead, and silver, and which we got that here. Lead, mercury, and silver, which is good. Sorry, this is silver, mercury, and lead. My bad. And it says there's no precipitate absence of metal ions, so which is good because we know that these guys here are insoluble in this compound. The second guy here, group containing metal compounds which precipitate with H2S ions is going to be this chemical reaction here, and it's going to, in the solution, are chromium, iron, and zinc here. And we know that because if we look at our solubility table, we look at S here, and these guys are all insoluble, right? If you go back into the chart here and I cross out mercury, you cross out silver, and you cross out our lead here, and you cross out all the ions that are group 1 to an ammonium. So for example, barium is crossed out here, lithium, magnesium, and so on. You would be left with zinc 2+, you're left with chromium, and you're left with iron here, which is correct. Where's iron? Fe2+. So that's the basic solution in the third one here. And then there's finally the sodium carbonate solution here, which I denote it as this guy here. The presence of this is going to be, if you look at the carbonate ion here, it's going to be this guy here. Everything's insoluble except group 1A and ammonium, right? So we're looking at chemicals that could be in group 1, that cannot be in group 1 because we're looking at precipitate here. So in this case, it would be whatever is left, right? So you have chromium, iron, and zinc, and then I think I mixed this up. And then the H2S ions here are mercury, tin, antimony, and cadmium, right? Because this here we're looking at the S2 minus here, and we're looking at all the metals that are not in 1, 2, and then for the basic solutions here, we have chromium, iron, and zinc. And then finally, with the sodium carbonate solution, we look at CO3, and we look at everything's insoluble except group 1. So this question really is, so the only thing that's left are the group 2 elements here. So basically, that's kind of the question. So the solution here is correct. But what we're doing here is we're basically kind of breaking down the logic behind solubility. And when we look at this question more carefully here, we're still looking at we have different mixtures here. So we have acidic solution, we have a normal solution, and we have a basic solution here. Yeah. And what we're doing here is we're looking at, what are we reacting with? We're reacting with HCl. What are we reacting with? Reacting with hydrogen sulfide, and we're reacting it with a basic solution with all of these guys here. So you can think of it as you're reacting some type of metal cation with an acid with a base or with a H2S, and then we're reacting with a sodium carbonate, and you're seeing which one actually precipitates out of the solution. So that means you know that it's insoluble, and which of these compounds are indeed soluble in water here. So, for example, your reader here says, finally, the solution was treated with sodium carbonate, which resulted in no precipitate. No precipitation just means it's going to be fully in solution, so there's no precipitate in the solution, so everything is soluble. So we're basically just going to look at the carbonate here, which is CO3. So it's insoluble except group 1A and NH4 here. So basically, we have to look at the compounds to think about which ones here are group 1A here. And we can look at our periodic table if we wanted to figure out which of these metals belong in that group here. So that's going to be the solution for this problem. Solution is correct. So it's really testing your knowledge about the solubility rules. And usually you're actually given these solubility rules on a test. Like you're not really expected to memorize this, just because it is quite a bit to memorize here with all of these compounds here. So solution is correct. Okay. It says here, write the chemical equation when sulfuric acid reacts with sodium hydrogen carbonate. So we have sulfuric acid, and we have sodium hydrogen carbonate. I think they meant to write sodium bicarbonate, but that's okay. So sulfuric acid here. So what we're doing is we're going to first write the chemical equation, right? So we have sulfuric acid, which we know here is an acid. So we know that we have some type of H. And if you dissect sulfuric acid, if you remove this ic acid here and you add H back, you're going to get sulfate here, which is SO4 2 minus. If you do the little crisscross with the 1 plus and the 2 minus, you're going to get H2SO4 as your chemical formula for sulfuric acid. And then sodium bicarbonate, I assume that's what they're writing here. If you break that down to ions, we have Na plus. And then I guess you have the H here in this case here. So NaH, the hydrogen here. And then carbonate, simply just CO3. So this is NaHCO3. So now you have both of our guys here. So we have we can write our balanced chemical reaction, right? We have H2SO4 plus NaHCO3. It's going to react to form, well, what is it forming, right? So this simply is a double displacement reaction here. So if Na here is going to go with this sulfate here. So we have Na2SO4. So this is sodium sulfate plus I have H going with the CO3 minus here, which is going to make carbonic acid. So H2CO3. And in reality, actually, H2CO3 breaks down into water and carbon dioxide. So if you wanted to, you can actually rewrite this as also Na2SO4. Plus we have carbon dioxide, so CO2 plus H2O. And what we can do is we can balance this chemical reaction, right? So I believe only a 2 is required here. Because we have 2 sodiums on the side, we have 2 sodiums on the side, so I write a 2 here. I have 1 sulfate, which is good. I have here 2 plus 4 here, so this has to be a 2 as well. And this is here is our balanced chemical reaction for this problem. You have 2 HCl, 2 Na2 plus, that's good. 2 CO2 and 2 H2. Oh, okay. Oh, yeah. Let me rewrite this actually, because I want to rewrite this as these guys here, CO2 and H2O. But I don't know if you're really going to need to know that, just because you don't know if carbonic acid actually breaks this down. So let me rebalance this. So we have 2 Na plus, 2 Na and 2 Nas here. We have 2 CO3s. And then we have H2 here. So we're going to have 2 H's, and then we're going to have 2 carbons here, which means I'm going to have to put a 2 here as well. And then I'm going to also have, so this makes actually 4 hydrogens here. So I'm going to have to put a 2 here, because I have 2 plus 2, 1 times 2 here, which is 2. So I'm going to have to add a 2 here as well. So this here is about a balanced chemical reaction. We have sulfuric acid plus 2 sodium bicarbonate, which is a sodium sulfate. Sodium sulfate plus 2 CO2 plus 2 H2O. So this is the correct. So this solution here is correct, because they give us the balanced chemical equation here. Actually, so this question's a bit lopsided here, so let me rewrite this guy. So this is for each molecule, specify the polarity of the bonds and the overall polarity of the molecule. Okay, so let me write this down. And then have H bond OH. Okay, it's asking, I want to know the polarity of the bonds and the overall polarity. So let's look at polarity of the bonds first on this compound. So bonds and then the molecule. Bonds and the molecules. So it's polar and non-polar here. So we're looking at first this guy here, right? So we have, this is BeCl2, beryllium chloride. And what we're doing here is we're looking at the bonds first. So we're looking at specifically the beryllium and chlorine bond. You can visualize it as either this guy here or this guy here. Either one works. It doesn't really matter how you visualize this, but I'm going to redraw this as Be bond Cl. And if you look at these two compounds here, one beryllium exists on the kind of the left side of the periodic table, and chlorine exists on the other side of the periodic table, which means the electronegativity difference, as we know from our periodic trends, is going to increase as we go across a period. So, which means we know that these two compounds actually have a dipole. We know that this here, chlorine, is pulling electron density away from this beryllium, which means for the bond itself, it's actually, this here is polar, because we have a polar bond between these two guys here, right? The dipole is pulling electron density away from this beryllium here. So this will result in a polar bond. Again, chlorine is much more electronegative than our beryllium here. And then in terms of our molecule though, if we look at our molecule, let me do this in red or something like that. The chlorine here is on both sides. So it's actually going to pull electron density this way and also this way. But this means that these dipoles actually cancel out, right? So I have a dipole moment going this way and it's going this way. So these two guys are going to cancel out, which means this molecule here is actually non-polar. So polar bond, but non-polar molecule here. And let's look at our, this here is H2O. Again, HOH here makes H2O. If we look at our bonds here, we have our oxygen bonded to our hydrogen. And then we have oxygen with these lone pairs here. As you can see, if you go back to your periodic table, hydrogen belongs here, oxygen belongs out here. Very, very big electronegativity difference. So the oxygen is going to pull electron density away from this hydrogen here, which means it results in a polar bond. And then for the molecule itself, if you look at this molecule, I have, again, oxygen is this negative charge here. It's going to, and the hydrogen has these partial positives here. It's actually going to pull away from this water molecule here. These lone pairs are actually going to shift the geometry. So it's actually not linear here. Water is actually drawn like this because these lone pairs want their space here. So in this case here, this guy is also a polar molecule because these electrons are moving away from this hydrogen. There's a net dipole pushing this way in terms of the partial negative on water here. So this is also a polar molecule. So as you can see, polar, non-polar, which is good, and then polar and polar. So the solution here is correct. This is number 3. Number 4, which of the first 20 elements on the periodic table are metal and which are non-metals? So let's this is more so an inspection kind of question here. First 20 elements, metals versus non-metals. So look at our periodic table here. We have hydrogen and we have helium. Let's look at these two elements first. These guys here are indeed non-metals, right? Hydrogen exists in a gas form. And helium also exists in a gas form here. So hydrogen, helium. Our next two here is lithium and beryllium here. And these guys here are indeed metals. You can think of them being metals as because they exist on this side here. So lithium, beryllium exists here. Sodium, magnesium are also metals. So Na, Mg. And then finally potassium and calcium for 19 and 20 here. And then everything else on this side of the periodic table is a non-metal here. So, and this is the exception to hydrogen here is the only exception because this here is a non-metal. So hydrogen, helium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then aluminum, silicon. Or well, actually aluminum and silicon here, and these guys here actually belong in the metalloids kind of section. So I don't know if maybe I should put that in the middle. So let me put boron in the middle as well, because boron here is a metalloid. You can notice that by looking at these guys here. Yeah. So let me see if I can look at the metalloids here. It kind of creates this little staircase here. This here is kind of the metalloid section here. So I don't know if they want to include that in our non-metals here. So maybe I'll just remove it here as well. Because then they both have metal and non-metal properties here. So we have hydrogen, helium, carbon, nitrogen, oxygen, fluorine, neon. We have phosphorus, sulfur, and chlorine. and argon here. So these guys here are specifically nonmetals, and we have some metalloids here, which is boron, silicon. So these guys here are the metalloids. So here it says first 20 elements. They listed out of 20 elements. So we have lithium, beryllium, sodium, magnesium, aluminum, potassium, and calcium. So aluminum here is actually a metalloid. So I don't like really how they put this guy here. And then elements are neither nonmetals. So these are metalloids. So boron, silicon. That's why I not put this here, which is good. Aluminum is here. Let me see if I can maximize this here first for you to see. Aluminum here is post-transition metals. So I guess in this case here, this one would be considered a metal. So boron, silicon is kind of the cutoff here. This kind of like staircase is the cutoff, and aluminum you could think of this as as kind of a post-transition metal. So these entire here block are transition metals, and this aluminum here would also be our a metal as well. So I'm missing aluminum from my chart here. So aluminum. So the solution here is correct because they actually included aluminum, whereas I didn't. Okay. As number 5. So for each of the following cases, identify the order with respect to the reactant. So case A, we have this is actually really order 1. The half-life of A decreases as the initial concentration of A decreases. So half-life of A decreases as the initial concentration decreases. B here says a 2-fold increase in initial concentration leads to 4 times the rate. C, this is a 2-fold or a 2 times increase of concentration leads to a 1.41 increase in rate. And 4, this is D, the time required for A to decrease from A0 to A02 is equal to the time required for A to decrease from A0 to 4.5. Rate of decrease of A is constant. Increase of A is constant. So let's look at the first statement here. It's asking us which of these ones are we want the order of the reactants, right? And we know that the order here, rate equals K times A here. So we have K, which is some type of rate constant, and we have A, which is the concentration of our reactants to the power of their coefficients. So this here is going to be the order, and we write X here. This here is going to be the overall order of our reaction. So it says here the half-life of A decreases as the initial concentration decreases. So I'm decreasing A here. So A here is our initial concentration. And it says here as the half-life of A is going to decrease as concentration also decreases here. So we're looking at and we're looking at basically the concentration, which is given as A here. And then we're looking at the half-life of A is also decreasing as well. So let me just find you the formula for the half-life here, because I don't know it off the top of my head. So half-life of a reaction formula. Again, you should be given these formulas of the test anyways, so I don't bother to memorize them as well. So we have half-life, which is T half, is given as the initial concentration over 2K. And this one would be, this here, it would be a, this one would be a zero order. So the half-life of A decreases as the initial concentration decreases. So in this one here, if we follow this kind of reaction here, this one would be a zero order. So A here is a zero order, because if we decrease our initial concentration in this way, our half-life is also going to decrease as well. So in this case here, this will be a zero order, and this is here is a zero order for our half-life. This is the formula for the zero order, which is good. Says here B, a twofold increase in the initial concentration leads to the rate of 4x, right? So if I'm increasing this by 2, what is my rate going to be? It's going to be 4 times. So I can put 4 here as the rate times K of A, and this here would be a x here, right? And I'm increasing the total concentration by 2. So this would be a 2A to the power of x. So what's x here? Well, x is simply just 2 to the power of x equals 4, right? And that will give us 2, because square root of 4 is 2. So this here is going to be the second order, which is correct here. So this is the second order. C here is a 2x increase of concentration leads to a 1.41 increase of rate. You could also visualize 1.41 as the square root of 2 here. I believe that's the square root of 2. Let me just check that for you. Yeah. So you can think of it as 1.41 is root 2 here, increase in rate, times K times, this is 2A to the power of x here, which means I'm going to have 2 to the power of x, which equals 2. Or you can write root 2 as half here, which means x here has to be equal to half. So this here is going to be a half order. And then finally, for 4, it says the time required for A to decrease from A0 to A0, half of that is equal to the time required for A to decrease from half to 0.4.5. The rate of decrease is constant. If the rate of decrease is constant, then the concentration here does not even matter in the first place. So if I'm decreasing this and it's not affecting the rate here is going to be the same, then this has to be in the 0th order. So rate only depends on your constant here. So this here says this is the big giveaway. The rate of A, decrease of A is a constant. So this here is the constant K, which means the order here, x is going to be 0, the 0th order. So the solution here is correct. Okay, that was number 5. Number 6, identify which sets of quantum numbers are valid for an electron. Each set is ordered. So there's not really a question here because I don't know which element I'm focused on here, but this is number 6. I'm going to see if I can reverse engineer this, or I guess to give you some examples here. Maybe I'll just describe what quantum numbers are. Maybe that's a little bit easier for us to figure out here. So we have n. We have numbers n. We have l. We have m subscript l, and we have m subscript s. So n here is going to be our principal quantum number. And this determines the number of shells that our electron has. So n could be 1, 2, and so on and so forth, like they did here, which is great. L here is the orbital, or the subshell. subshell slash orbital. And L has to be basically n minus. L has to be from, it can be from 0 to 1 all the way up to n minus 1. And this determines the orbital here. So this is either S, P, D, or F orbitals. For example, if you had an element that had a principal quantum number of 2, that means my subshell is going to be from 0 and to 1 here. So 0 representing the S orbital and 1 representing the P orbital, which is correct here. So you can have either exist in the S orbital or the P orbital. ML here is the specific orbital here, or though you can think of it as the magnetic number. And ML here is going to equal basically plus or minus L here all the way up to, so it's going to go to minus L to 0 and then to minus L here. And this here is going to be that's going to be your magnetic quantum number. And then finally you have MS here. And MS, we don't really talk about it that often. It's more so just a spin number here. And we don't really talk about this much often because it's either half or negative half for an electron here. And for a different particle here, we have different spins, but don't worry about it. More so that. So we have kind of these four guys here. So we have principal quantum number, we have the orbital, we have the magnetic quantum number here, which is basically the number of orbitals and their orientation. So from a negative L to, oh, this is positive L, sorry. And then we have our spin number, which is half and negative half here. So I believe that this here is a good enough solution. I think this is supposed to be L, but I don't think they did it here. So valid sets here, so they have 2 here, which is our principal quantum number. 1 here will be our subshell, so it'd be 1. 1 can also be a magnetic quantum number, and the half is going to be our spin number, which is good. So checking the first example, the solution is correct. So that's a valid set for a quantum number here. Okay. Let's look at number 7. It says, what is the pH of a 0.100 molar solution of NaC2H3O2 when the Ka is 1.8 times 10 to the negative 5? So we have NaC2H3O2. It's going to dissociate into Na plus C2H3O2 minus. And then what's going to do with this here, this is just simply sodium ions. We don't really care about that, but we care about this guy here, C2H3O2 minus plus water. It's going to be in equilibrium with HC2, sorry, H3O2 plus this would be OH minus, because the hydrogen is going to be donated to here, so this is going to be OH minus, and our Ka is 1.8 times 10 to the negative 5. So let's see if they wrote that first. Yeah, we're working on this solution, right? Because this here is not the correct solution here. Yeah, so this solution is actually this solution is the wrong solution for this problem here, because I think they meant to answer this. They answered the wrong problem here, because I was looking at this problem here. I believe that they answered the wrong problem here. So I immediately know off the top of my head that this solution here is going to be incorrect. But nevertheless, I think what we can do is we can actually solve this problem as well and see what number we get here. So I have a 0.100 molar solution of this guy here. So what we have to do first, we have to do, we want to know the pH of this guy. So let's solve for the pH. So I have 0.1 here. I'm going to have also 0.1. So this starts with 0.1 molar. What we can do is we can do an ice table, and we can figure out the concentration of this guy here, and then we can plug it into Henderson-Hasselbalch. So this is 0.1 molars. This here is 0, 0. We don't care about water here. 0.1 minus x, positive x plus x here. 0.1 minus x plus x plus x here. So we have our ice table here, and what we can do is we can plug it into our, instead of the Ka value here, because we're actually getting hydroxide, we want to know the Kb, right? So you have to relate it actually to Kw here. Equals Ka times Kb. So Kb is going to equal Kw divided by Ka, which is going to be base Kw here we know as 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So we get 5.5. 6 times 10 to the negative 10. That's our Kb. This is going to equal our concentration of our products times the concentration of a reactant. So we have x squared, so these two guys here, times 0.1 minus x. I'm going to use the assumption method and it cross out this negative x here. So I'm just simply going to multiply both sides by 0.1 and square root it. Which means x is going to be 7.453 times 10 to the negative 6. And this is the concentration of our hydroxide ion here, which means our POH is simply just, POH equals negative log of our hydroxide ion here. So negative log of this guy, which is 7.453 times 10 to the negative 6, which is going to equal negative log of answer. It's 5.12. And then we simply just do, for pH, we know that 14 equals pH plus POH. So 14 equals pH plus 5.12. So pH is simply just 14 minus 5.12, which is going to give us a value of 8.87. And this solution would be this solution here as well. So it would be B. So this is definitely the incorrect solution. Solution is incorrect because it's stating the wrong solution for the above problem. And I'm just going to write my solution as well. So we have C2H3O2 minus plus H2O. It's going to give me, that's my equilibrium sign here, HC2H3O2 plus OH minus. So perform or draw a dice table. So 0.1 to 0, also 0. I hope the formatting comes out nicely. And then from Ka, we can find Kb because we are producing hydroxide ions, which means our equilibrium equation must be in Kb. So Kw equals Ka times Kb. So that's going to equal, so Kb is going to equal Kw divided by Ka. And this here is set that's 1.0 times 10 to the negative 14 divided by Ka was 1.8 times 10 to the negative 5. and this I wrote as 5.56 times 10 to the negative 10. Yeah. Which means I can write that Kb is equal to the concentration of our products times OH minus divided by our concentration of our reactants. So HC2H3 O2 minus so if Kb is going to equal x squared divided by 0.1 minus x by assumption method, we can remove x. We can say that so therefore we can get this equation, but without this x here. X squared is going to equal 5.56 times 10 to the power of negative 11. X is going to equal 7.453 times 10 to the negative 6 molars, which will equal our concentration of our hydroxide. And then by solve for POH, POH is going to equal negative log of the hydroxide ions negative log of 7.453 times 10 to the power of negative 6. POH is going to equal, I had here 5.12, and solve for pH. So 14 equals pH plus POH, 14, so which is pH is going to equal 14 minus POH minus 5.12, which is going to equal 0.87 here. So solution is B. So solution is incorrect because they actually wrote down the wrong guy here. All right. Very long question. That was question 7. Let me do maybe 1 or 2 more. We'll call it a day. Let's do 1 more actually. We'll call it a day. This is number 8 here. So it says classify each structure according to its functional class. Oh, that's the previous question. So I have here the first question is A. So I have this structure here. I'm going to draw the line diagram here. It's asking us, okay, what is the functional class? Well, the functional class is have basically all alkanes except for the C double bond O. And as you can see, it's either an aldehyde or a ketone, right? So an aldehyde would be a carbonyl group in the primary carbon, in the first carbon here, in terms of in the beginning of the compound, and the ketone's in the middle of the compound. In this case here, it's in the middle of the compound, which means this here is a ketone. It's a carbonyl group. Our second compound here is CH3 to 1,2 bond O bond CH. I have ethyl here, bond again, bond again, bond again. So that's our compound here. As you can see, everything's alkane except for this O group here, and it's linking 2 single bonds together. So this here is going to be a ether. Because again, an ether is comprised of this ROR here. So this here is going to be ether. This is bond end. Double bond O here. So I have this guy here. I have here this double bond O, but I also have an N here. So this here is going to be an amide group, because I have a C double bond O bond to N here. As you can see, this guy here is the amine, and this will be our carboxylic acid here. So this here is an amide group. And then finally, this guy here is simply an amine group here, because I don't have the C double bond O, but I do have the nitrogen here. So these are my solutions: a ketone, a carbonyl group, an ether, an amide, and an amine. So a ketone, ether, amide, and amine. So solution here is correct. Good analysis. Now let's see if I can do one more question, if possible here. This is number 9. So what is the pH of a 0.100 hypochlorous acid solution here? Okay, so hypochlorous acid is HClO plus, I'm going to add H2O, sorry. It's going to give me ClO minus plus H3O plus. And then my Ka here is 3.5 times something. Let me just Google what the Ka of HClO here. Let's see. 3.5 times 10 to the negative 8. That's our K value. Okay, so it's finding out what the pH is. So simply we have to do is ICL, right? So ICE. Our initial concentration of hypochlorous acid is 0.1. We don't care about the water again. So here is 0, 0, minus x plus x plus x, 0.1 minus x, x, and x here. So what we can do is we can write out our equilibrium equation, right? So we have Ka, which is 3.5 times 10 to the negative 8. It's going to equal the concentration of our products, so ClO minus and H3O plus our reactants, which is HClO. It's going to equal x times x over 0.1 minus x. So it's going to equal x squared over 0.1 minus x. Now, as you can see, I can do the assumption method. I can cross out this x here because this, I'm assuming that this is very, very small. So which means I'm going to get 3.5. If I move 0.1 to the other side, times 10 to the negative 9 equals x squared. I can square root both sides. So x here is going to equal 3.5. 3.5 times 10 to the negative 9. It's going to equal 5.91, or 5.92, sorry, times 10 to the negative 5. And this here is also equal to the concentration of our hydronium ion. And finally, what we can do is we can solve for the pH, right? So pH is simply just negative log of our hydronium ion, which means that we know it's 5.92 times 10 to the 5 molars here. So pH is simply just the negative log of our concentration of our hydronium ion, which is going to equal 4.23. So this solution here is correct because they had 4.23 as the solution. As you can see, 0.000592 is 5.92 times 10 to the negative 5. So this solution is correct. Good analysis. So with that, I've finished probably about 9 problems today for our solution, which is pretty good. I couldn't get to the last question, that's okay. Again, thank you so much for watching this stream. If you like the stream, definitely check us out on youtube.com/OneClass. Oh, I actually could read your comments. I'm sorry. I had my chat kind of turned off, so sorry about that. I didn't actually look at the comments while I was doing that. But again, thank you so much for this stream. Again, if you like our channel, definitely check our OneClass channel on YouTube at youtube.com/OneClass. You can check us out. Again, my name is Joey. I stream actually I only stream 2 days a week now. I stream Mondays for math and Wednesdays for chemistry, so you can catch me there. Again, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.